Hello everyone and welcome back. So today we're moving on from just talking about discrete probability distributions generally to actually talking about discrete probability distributions in a specific way, and this is related to the binomial theorem. Now this is still a discrete probability distribution. Hopefully you all actually remember what it means for something to be discrete, in that it can only take particular number values. So again, we can only have certain values. Okay, quite often with binomial we're talking about whole number values. So let's get started and examine exactly what the binomial probability distribution is, and more specifically when it is that you can use this distribution. Now, we use the binomial probability distribution when we see something called a Bernoulli sequence. So the properties, we need to look for particular properties of our Bernoulli trials, and this indicates to us that we're going to be able to use our binomial probability distribution to work out the answers. I have some confidence that a lot of you will find this a lot better than the discrete probability we've been considering so far. Okay? So the first thing that we look for is that there are only two possible outcomes, success or failure. So what we mean by that, for example, it could be that you win a game. In that case, our failure would be that you do not win. I'm not going to say lose because that doesn't take into account a draw. Okay, so either you win or you don't. Another option could be it rains on a particular day. What would failure be? That it doesn't rain. Okay? In terms of rolling a dice, it could be that we roll a 6. Our failure then, our corresponding failure, would be that we do not roll a 6. Hopefully you see what we're doing here. So success and failure, it's either that the event occurs, which is success, the event occurs. So I might write that here as well. Generally what we're saying here is that our event that we're interested in actually occurs, it happens, and our failure is when our event does not occur. Alright, so that's our first property we look for that indicates to us that perhaps we are seeing a Bernoulli trial, perhaps we can use the binomial probability distribution. Our second property is that the probability of success, which we denote, we use a P to represent it, and failure, which we use for Q, do not change. So that means that every day the chance of it raining is the same as the chance that it doesn't, the chance that it rains is the same, and every day the chance that it does not rain is the same. It does not depend on what came before. Okay? Came before. So that means that if we are using selection, if I am selecting people for an activity, if I am selecting marbles out of a jar, if I am selecting chocolates out of a box, it is selection with replacement. I will take something out and I will put it back in again. So therefore the probability of choosing that particular marble or that particular chocolate will not change, because as soon as I take it out, I put it back in. So again, there is the same chance that I might select it again. Our third property is that no one trial has any effect on another, which is what I was saying before. And this really relates into the fact that the probability of success and failure do not change. So what this means is that there are n, so this can be any number, okay, any number of independent trials. One trial does not affect the next. So even if we see these properties though, that is not necessarily enough for us to decide that yes, we want to go ahead and use the Bernoulli sequence or the binomial probability distribution. So we need to think about when would we actually use the binomial probability distribution. So to start with, we need these properties here we spoke about. We need only 2 possible outcomes. We need the probability to not change, that's our second one, and we need the trials to be independent. We also need to be dealing with discrete data. Like I mentioned before, we do indeed need our data to be discrete. But there are a couple of other things. We also use this when we want to know how many times something happens. So we're trying to work out the probability for the number of times the event will occur. Let me give you an example for that. I might say, I'm going to roll the dice 20 times. I want to know the probability that I will get a 6 5 times. First of all, we've got only 2 possible outcomes, so I'm suggesting roll a die 20 times. Probability that we get 6, we wanted to know what's the chance that occurs 5 times. If we think of our different properties, only 2 possible outcomes, success or failure. Well, that one fits. We could get a 6 or not a 6. Probability of success and failure do not change. Well, probability of getting a 6, each time I roll the dice, the chance of getting a 6 will be 1 over 6. That's not changing. The result of one trial has no effect on the other. Well, that fits because it doesn't matter what happened the first time I roll the dice. The second time, I still have a 1 out of 6 chance in getting it. That hasn't changed. Is it discrete? Yes, it is. The number of 6s, they can only be whole numbers. This next criteria here, I want to know the number of times an event will occur. Well, yes, that's what I'm doing. I'm trying to find out the probability that I will get exactly 5 6s. Okay? The final thing we look for, and this is very important, is that order does not matter. Okay? So to use the binomial distribution, we use it when we do not care where these 6s occur. If I knew specifically that I wanted to have a 6 and then not a 6 and then not a 6 and then a 6 and then not a 6 then not a 6, if this was the case, I could not use binomial. Okay? If order matters, this will not work. But I'm not saying that. I'm just saying we need to have 5 6s. I don't care if they're the first 5, if they're the last 5 numbers rolled, if they're all mixed up together. Order does not matter, so that's why this works and we can use the binomial theorem. Alright, let's actually look at the formula. And there is a nice formula that we can use for the binomial distribution. Okay, when we recognize something is binomial, this is what we can use. N, this will be no surprise to you, is the number of trials. So in my example from before, I would have had N is 20 because I was rolling my dice 20 times. P is the probability of success. So again, in this case from before, the chance of me rolling a 6 any one time is 1 out of 6. So that would be my value of P. Q is the probability of failure. And we can also write that, the way we figure that out is by doing 1 minus our probability of success. And X, this is what we want to figure out. This is the probability that we are calculating, okay? Oh, sorry. So this here is the number of times we want the event to occur. So for my previous example, we would have had X would be 5, we wanted to get 5 6s. We would have had N was 20, we were doing 20 trials, and we would have had P is 1 over 6, and we would have had Q is 5 over 6, and we would be able to put that into our formula. Now in terms of the formula itself, this part is straightforward. Our probability of success to the power of X, the number of times we want our event to occur. Q to the power of This is essentially the number of times we don't want our event to occur, the number of times we don't want it to occur. Now this part here, the n choose x, this is why we talked about counting methods earlier on. If we are going to work out n choose x, our formula, you might remember this from when we did counting methods, is n factorial over x factorial n minus x factorial. Okay, so this was when we did our combinations or our selections. We're saying how many ways can I select x number of items from n possible trials. Okay, this is when order doesn't matter. Very, very rarely they ask you to do this in a tech-free exam, which means you actually do need to know how to set this up and how to work this out. And so that's what we're going to look at first. So let's have a look at our first example. Okay, so for our first example here, we've got an urn contains 3 yellow and 7 black marbles. 4 marbles are drawn at random from the urn. Now, if you're not sure what an urn is, it's essentially just a vase or a container of some kind. Here's my urn. Within it here, I'm even going to draw this, I have 3 black marbles and we have, 3 yellow marbles and we have 7 black. 1, 2, 3, 4, 5, 6, 7. Okay, there's my lovely urn with 3 yellow and 7 black marbles. We are drawing 4 marbles at random and each is replaced. This is important before the next is drawn. So let's think back to our criteria before. Our first property was talking about, oh gosh, can I even remember now? Do we have only 2 possibilities, success or failure? Yes, we do. Either we can draw a yellow marble, that would be success. Okay, so in this case, our probability of success is going to be having a yellow marble because that's what we're interested in finding out. That's what we're looking for here. Does the chance of it being a yellow marble change? Well, every time I put my hand in this, if I'm selecting randomly, because it says randomly, every time I put my hand in this, there are 3 yellow marbles out of 10. I have a 3 out of 10 chance of choosing a yellow marble. Because it's replaced each time, that probability does not change. Are they independent trials? Yes, they are, because I'm putting them back and drawing them randomly each time. So I've met my 3 properties for a Bernoulli trial. Then we want to say, am I finding out how many times something occurs? Yes, because I'm wanting exactly 1. And finally, does order matter? No, I don't care which marble is yellow, just that I get 1 yellow marble. So how we set this up? We start by saying, listing what we know. N, our number of trials, we are drawing out 4 marbles, so N is equal to 4. P, our probability of success, we worked this out before, was 3 over 10, which means that Q, our probability of failure, is 7 out of 10. Our value of X is 1. Now we should always start by actually defining X. You need to tell me what X represents. In this case, we let X equal the number of yellow marbles. Okay, that's what we're trying to calculate. So for part A, what we're doing is we're working out the probability that X equals 1. If we set this up according to our formula, which you would have up further in your sheet, the way we do this, we're going to have N choose 1, our probability of success, how many times do we want successes? 1. Our probability of failure, how many times do we want not yellow marbles, or how many times do we want failure, is 3. Now, if we had this in the unfortunate situation of a tech-free exam, we would have to actually work this out. 4 choose 1, that means I've got 4 factorial over 1 factorial, and 4 minus 1 factorial is 3 factorial. Times 3 over 10 times, let's work out 7 over 10 to the power of 3. 7 to the power of 3 is 343, and you can always write it down to work it out if you need to. 10 to the power of 3, we have 3 zeros. Working out this, 4 factorial means 4 times 3 times 2 times 1. 1 factorial is 1. 3 factorial is 3 times 2 times 1. I can cancel out. I'm still multiplying by 3 times 10. What I have got now, okay, what I've now got, let's cancel our 4. 4 goes into 4 once. 4 goes into 1,250 times. So what we're going to end up with in our denominator, 250 times 10 is 2500. 3 times 343, I'll just tell you for sake of speed, is 1,029. But if you get this in tech free and you're not sure, you would write it out like so and work it out, do our normal multiplication, okay, which we should all be aware of how to do. So that's it. That's all there is to it. Now, let's have a look at B. For option B here, we are going to be working out the probability that more than 2, that x is greater than 2. Now, if we think this out, we've got 4 marbles being drawn. If we want more than 2, that means we either want x to equal 3 or we want x to equal 4. So we have to set it up twice in this case. 4 choose 3. 3 to the power of 10, 3 over 10 to the power of 3. 7 over 10 to the power of 1. And now I'm just substituting directly into our formula here, okay? Directly into the formula. And again, if this was in tech free, you unfortunately would have to work this out by hand. I'm just actually going to quickly get my calculator up and show you how we would do this were we to actually use the calculator, okay? Hold on just a second. So if we're in our calculator, to select this, remember in order to do NCR, we need to go to the advanced section here, and here it is. We want to have 4, choose 3, and we are going to multiply that by, we now have 3 over 10, which we can write as 3 over 10, or it's the same as 0.3, and we're going to do that to the power of 3 multiplied by 7 over 10, or 0.7. Plus, we also have, we've got to go back to our NCR, choosing our number of selections just here. We've got 4 choose 4, which hopefully you know there is only one way to successfully choose 4 objects from 4 items. 3 over 10 is the same as 0.3 to the power of 4, and then 0.7 to the power of 0, well, we know anything to the power of 0 is 1. Put it in our calculator and we get our answer of 837 over 1,000. So let's just pop back in here. Now, as you might have noticed here, so our answer therefore, my pen's changed colours, well, there's worse things, 837 over 10,000. As I said, you can calculate this by hand as well, using the same methods we did for this first example, and I would encourage you to practice that as it does come up occasionally on the exams. Much more likely though is for us to use this in a tech active situation. And there is actually an even better way of doing this using our CAS calculators, and that's something that I will get to in just a little bit longer. A couple of key words first. When we're setting up binomial, we need to be very, very careful of which words and therefore which symbols we use. If we say at least, it means that we include that value. That's why we've got greater than or equal to. More than or greater than means that I do not include that particular value. That's why we have just the greater than sign. Fewer than or less than, we do not include the value, everything smaller than the number. No more than, that means everything smaller or including the number. And exactly, we've got our equal sign. This is really important that you can set up your equations correctly, otherwise you will not be able to get the correct answer. What I want to do now is to look at an example of how we would actually use our calculator for this. So on our calculator, if we just want to calculate the probability that x equals k, so we're just looking for a particular value, that means that all I would do is I'm just actually working out this probability. So I'd be doing that n, choose k, p to the power of k, q to the power of n minus k. Alright. When I do that in our CAS command, it's something called binomial PDF, and I will show you this in a minute, but it is really important we get that right. If I'm wanting to know the probability x is less than or equal to k, that means I'm going to be working out a huge sum, probability x equals 0 plus probability x equals 1 plus it keeps continuing all the way up to probability x is equal to k. So k was 5, I'd be doing probability x equals 0, 1, 2, 3, 4, 5. When I do this, I use something called binomial CDF. I should point out, PDF stands for probability distribution function, and CDF, I'll write it over here, stands for cumulative distribution function. So cumulative, that's more than one thing. We're grouping together more than one probability, which is why I've got this sum here. When we do this, we're going to have to enter something with our lower and upper bounds, and I think I'll wait and explain that later on. Probability x less than k. We still start at x equals 0. We still start adding all of our values, but in this case we stop one spot before k. I can't get up to whatever that is, I can't include k, so my largest probability will be the value of, what am I doing, not x. Let me just rub that out there. Okay, what we're doing is the value of k, that x will equal k minus 1. We stopped the one before. Once again, because we're adding together more than one probability, we're accumulating them. So it's again binomial CDF. If we're greater than or equal to k, that means we start at our value of k. Our next one would be our value of k plus 1. And we keep going until we get up to our biggest possible value, which is however many trials, however many times I'm doing this. That's our biggest possible value. Once again, we're adding a whole lot of values together, so we're once again using our cumulative distribution function. X greater than k, we start at, we don't include k, so we've got to start at one number past k. And then we would have our next number past k. And then we would keep going, once again stopping only at the total number of trials. And again we use binomial CDF, which is for our cumulative probability distribution function. Alright, examples. So, probability that James scores a goal in any one attempt is 0.4. So this is our probability. Find the probability that out of 7 attempts, James scores a goal a certain number of times. First of all, we have only two options, either success, he scores a goal, or failure, he does not. Secondly, the probability of success does not change, and it doesn't, it is always 0.4. Our third property is that the trials are independent, and they are because the probability that he scores a goal in any one attempt is this, regardless of the other attempts. Are we wanting to know the number of times something happens? Yes, we are. 3 times. Do we care about order? No, we do not. So this is what we want. How we set this out. The first very important thing is that we need to define a variable. So I let x, or you could use y, but x is quite common, let x equal number of goals scored, because that's what we're interested in finding out. For part A, we've worked out here our probability is 0.4, our number of trials is 7. We write probability x equals 3. This is what we're trying to find out. Now, this is very, very important. We must show some working out. The way we do this, because I'm about to do this entirely on the calculator, all you need to write, and we actually write it before our working out here, is that this is binomial. BI stands for binomial. We put a little squiggly line, and inside here we write n, our number of attempts first, comma, our probability, our p-value. This is your working out. You get a mark for writing that. So our notation is that we write binomial, squiggly line, n, comma, p. And that is 1 mark. That is for you showing that yes, you know it's binomial, you know how many the number of trials are, and you know the value of p. That's all you need for your working out. These are usually only 1 or 2 mark questions, because now we can put this straight in the calculator to get our answer. So excuse me for a second as I get my calculator up to show you. Yes, I do want to keep the ink. Okay, the calculator. So this is much better than the other way. We click interactive, distribution, discrete, okay, because we're doing discrete probability still at the moment. And here are the 2 options I was talking about before, binomial PDF or binomial CDF. Because we are dealing with our single value, our probability distribution function, we click here. Then we just enter things in. X is our, the same as what X was here, our specified trial, which is 3. Our number of trials n, well, we're doing this 7 times. Our probability of success, our p-value, and as it tells us here, it must be between 0 and 1, which makes sense, is 0.4. Okay? And we get an answer, and we write it down. That is it. What I would like to point out to you is that unfortunately, when we're using this, it gives our answers only as decimals. Almost always that is fine, and the question will tell you to give it to a specified number of decimal places. Very occasionally, very, very rarely, if you needed it in exact, then you would have to use the method I showed for the first example. So coming back here, we can then put our final answer in, which is 2903. And I am going to give it to 4 decimal places because that's most common. Part B, we show us again. We know it's binomial. Our number of trials is 7. Our probability of success is 0.4. It hasn't changed. We want to figure out the probability that he scores a goal at least 5 times. So that means we'd be happy if he scored 5, 6, or 7 times. So we do x is greater than or equal to 5. And we're going to work it out. Once again, we do it directly in the calculator. So once again, we get our calculator up and we go to interactive, distribution, discrete. This time we want binomial CDF. Our lower value, what is the smallest value of x we can have? Our smallest value of x is going to be 5. Upper, what is our biggest possible x value? Well, like I said before, if we have a look over here, our options were 5, 6 or 7. So our biggest possible x value is 7. The number of trials we're doing is 7. The probability of success is 0.4. We click OK, and once again we get an answer that is much, much easier to do than writing out all of those lists like we did in the first one. So again, we can come back here and we can write down our final answer. Let's put it correct to 4 decimal places because that is commonly what we need. Looking at our final example for today, Part C, we are still doing binomial probability. We want to work out the probability James scores a goal 6 times. This is what we're finding out, so we write our 6 times. Given that, remember this is how we notice conditional probability. We put our given that sign, he scores at least twice. X greater than or equal to 2. That's how we show at least twice. What we get using our conditional probability formula, remember it is in actual fact on your formula sheet. So this is what we're going to do. Now we have to clarify here, if we think of where these occur, x equals 6, x greater than or equal to 2. X greater than or equal to 2, the possibilities are the numbers 2, 3, 4, 5, 6 and 7. Which of those intersect with x equals 6? Only the number x equals 6. Now please, please be careful. It is not always, or rather not even often, the fact that whatever is here ends up in the numerator. It does sometimes, but is definitely not the case always. We then go to our calculator once again. Okay, let's come back here. So we've got to work out for the first one, probability x equals 6. This is going to be binomial PDF because we've got one particular probability distribution function. 6 is our value of x, our number of trials is 7, our probability of success is 0.4. And we can press OK. Probability x is greater than or equal to 2, we've got to use our our distribution discrete, but it's CDF because it's cumulative, more than one x value. Our smallest value that x can take is 2. Our biggest value x can take is 7 because that's how many times he's attempting goal. Our number of trials is 7 and our probability of success is 0.4. Finally, we're wanting to take our first value and we're going to divide it by our second one. Notice how I'm using the entire values. I don't want to use rounded values. I don't want to risk losing accuracy. We get an answer. I'm not going to give it as a fraction because we didn't have fractions to start with. And therefore, so our final answer is 0.0204. Now please note our probabilities we get, they always should be between 0 and 1. If they are not, it's an indication that something's gone wrong and you have to go back and figure out where the mistake occurred. This is pretty much it for binomial probability distributions. I think you'll like it once you give it a go. We definitely will discuss more in class. If you have any questions, make sure you bring them along and ask me. Thanks for watching. See you next time.